Good evening. My name is Sergey Tretyak. I will be chair of this session on the excited states, and we have a fantastic program. Irene Burghardt will start with a plenary talk, and then it will be followed by five 5-minute lightning talks. And let's start with our plenary lecture. Irene has been doing fantastic work. We're using rigorous high-level accuracy, which set up the golden standard for simulations of excited state dynamics in functional materials. Irene, the floor is yours.
Thank you very much, Sergey, for the introduction. This presentation is on first principles quantum dynamical simulations of excitonic dynamics, and quantum dynamical actually implies that we also treat the vibrations quantum mechanically. But first things first, I would like to thank the organizers and Jochen and his team to organizing this great workshop event. Okay, so we will have these three topics essentially. So I will first give a general introduction to like first principle simulation work in this area, like which methods work, and then we're going to focus on the Vibronic lattice Hamiltonians combined with high-dimensional quantum dynamics, which is what we are using. Then I will give two examples. One is about intra-chain exciton transport, like coherent or diffusive. And I will show how we move to a generalized Frenkel-Holstein type Hamiltonian, and we compute coherent torsion-induced exciton dynamics at finite temperature. And in the second application part, we'll include charge transfer effects. I'll say something about the coupling between Frenkel and charge transfer excitons and about interfacial exciton dissociation, actually in like vibrationally hot systems, but also in the case of cold exciton dissociation where the processes become very slow. So in general, the theory and modeling side obviously faces a big challenge. So these systems have a lot of electronic states. We have strong electron-phonon coupling. We have multiple non-adiabatic events, so many closely coupled electronic states. We have these aggregate type systems that are determined by the electronic properties together with the molecular packing effects. And then we have delocalization, we have charge transfer and excitonic couplings, and in the end we have the dynamics that essentially should be treated as coherent wave packet dynamics. So all this is extremely demanding. And key issues are like the adequacy of the electronic structure methods that we pick, especially if we go for excited states, so excitonic states, charge transfer states. And then if we want to include the dynamics, there is the issue of limited accuracy of on-the-fly trajectory-based methods on the one hand, and on the other hand, we have, in general, limited flexibility of exact wave function methods. So essentially, we have to find a compromise between these two directions. And as a result, we have essentially two types of approaches that are being used and that you can encounter in the literature. And also at this workshop, you already have heard about at least one of these two directions, the one on the left-hand side. So here the idea is that we do like on the fly coupled electronic nuclear dynamics, typically starting from time-dependent quantum equations, and these are coupled to an approximate representation of the nuclear dynamics using, for example, Ehrenfest or surface hopping type schemes. This is nice because we do not use any pre-computed potentials, but there are potential drawbacks because we possibly get a poor description of the excited states and also a poor description of the nuclear dynamics. And this motivates the use of alternative methods that are a bit more old-fashioned in the sense that they actually connect to many model Hamiltonians that are around in the solid state literature, materials literature. And these are like parameterized lattice Hamiltonians that we can combine with multi-state quantum dynamics, including the nuclei, so including the vibrations. And then we typically come up with this multi-state and multi-site Hamiltonian that we have to suitably parameterize. And we can combine that with quantum dynamics. So we get all the features like coherence, tunneling, and so on, zero-point energies in this context. So the advantage is clearly that we have like this physically motivated lattice type picture, and we can use quantum dynamics. But the drawbacks are that we often have to live with a restricted number of coordinates, and we have to produce this Hamiltonian, like typically from the adiabatic perspective, using so-called diabatization procedures. Still, this is the direction that I'm going to essentially comment on in the following. And right, so here is a picture actually illustrating the two types of systems that are at the center of this lecture. So this is an oligomer perspective. We're actually starting with electronic structure calculations for oligomers. So typically like chains that would correspond to so-called J aggregates, where you have this head-to-tail alignment of transition dipoles. And we also look at these stacked species, which would correspond to H aggregates, where we have like a parallel alignment of the dipoles. And that already suggests the type of lattice Hamiltonian we want. So we want to translate this kind of to a monomer-based representation. And then we use as much electronic structure information as we can, including the computation of energy levels, of course, and also information on the vibrations, as you will hear in a second, and also the characterization of the states. So we can use this transition density analysis to generate these electron-hole maps that tell us if the relevant states are actually of Frenkel type character, so essentially diagonal in this representation, and how they depend on conformational change. So here we have these torsional modes that actually show up here, actually literally as a conjugation break. So you see that the electronic density is diminished if we actually twist the molecule. So this analysis is very important, and all the more so if you get to the left-hand side, if you have an admixture of Frenkel states and charge transfer excitons, which show up in these electron-hole maps. So this essentially determines the type of model Hamiltonian that we're using. And in general, so the lattice models that we want are inspired by that picture of having the electron-hole representation and distributing electrons and holes over the lattice. So this model Hamiltonian is going to include Frenkel type states where the electron and hole as a basis function are located as a given site, and charge transfer excitons where we have charge separation, and also long-range charge separated species that you get upon exciton dissociation. And this is the type of Hamiltonian that we want to parameterize. So as already mentioned, from the electronic structure side, we don't just take like single point information, but we get information about the potential. So as a function of the important subset of vibrational coordinates. And there are different ways of doing this. So one approach is to use these so-called spectral densities. So the spectral densities actually correspond to a shifted harmonic oscillator model. There's also called linear vibronic coupling model that often captures the essence of what is going on upon photoexcitation. And we can actually get the information about the vibronic couplings or spectral densities from Frank-Hunter gradients, which is a pretty cheap way of doing things. Now, this is like this harmonic type picture. If we have like, slow amplitude motions, and so we have like torsion degrees of freedom, for example, then it might be necessary to include the unharmonicity of the potential. In this case, we actually do potential energy surface cuts that are then translated to the monomer-based representation, and we use mapping procedures to do that as a function of the coordinates. All right, and actually we are not constrained to just one dimension. So this type of representation also accommodates high dimensional and more complex topologies, conical intersections, for example. So this is a picture of like a conical intersection landscape that we analyzed quite a long time ago together with Eric Bittner in 2008. So this is a heterojunction system that we looked at the time. And so so conical intersections are going to show up repeatedly. I'm not going to talk so much about conical intersections in this presentation, but Sergei is actually devoting much of his talk on these topologies. Right, so we have like this parameterized lattice Hamiltonian, including the information of the vibrations, and now we can use this in order to do dynamics. Now we want to do like full quantum dynamics, which one could do either at the level of high-dimensional wave functions, like including the full electronic and vibrational space, and then one could derive like statistical properties later on in terms of these density operators. And this direction actually uses, for example, the multi-configuration time-dependent torsion method. That is the method that I will tell you more about in a second, but there are various other ways of doing this. Now, the second approach uses master equations. And you will need so-called non-Markovian master equations because everything is happening on the same time scale. And here, the so-called hierarchy equations of motion method is certainly one of the leading methods in the field. But for us, so the wave function-based representation is a very efficient way of doing this. So we use this multi-configuration time-dependent tertiary method, MCTDH, which represents a tensor approximation scheme. This means we have correlated wave functions in many dimensions, which are represented as sums over products. Now, this is a way to include correlations. And the key is that we actually break down the full time-dependent wave function into these subspaces that are represented by so-called single particle functions. And we have a time-dependent variational principle that is going to guarantee the optimal evolution of these single particle functions. This is why the method actually works for a large number of degrees of freedom, like tens or hundreds, I say. Now, the equations of motion are non-trivial. We have equations for the coefficients, which are coupled to highly nonlinear equations for the single particle functions. So this is pretty demanding, but still it's very efficient, and we can break the exponential scaling problem of quantum dynamics to some extent. Now, this is much improved yet if we move to a more refined version of the method that I'm essentially going to use in the following, the multi-layer MCTDH method. Here we can actually move to 100 or 1,000 modes and states. And that is an iterative scheme. So we have our wave function that is represented as a sum of our products. We have these single particle functions here. And these are again represented as sums of our products, just in the MCTDH way. So it's a repeated MCTDH scheme. And this ends up in a hierarchical format, which becomes very practical to use. And that is essentially what we are going to employ in the following. And just one last detail. So since we are going to use this for thermally activated dynamics as well, we're going to include thermal reservoirs. And in the simplest case, we can do this in terms of a stochastic like bath of modes. And so we're going to use importance sampling over like the phase space of these bath modes, and this is coupled to the quantum dynamics. And that actually creates a very, very flexible setup. Now, of course, from the perspective of trajectory-based methods, I mean, you may think this is kind of a lot of effort, and in a sense it is, of course, but the objective here is to actually capture quantum coherent evolution correctly, especially if short timescales are involved. And this picture illustrates it kind of, essentially. So we're thinking in terms of electronic coherence. So we have this wave function that is a superposition state. And then we have these wave packets that are running like on these different potential energy surfaces. And it's the overlap of these wave packets that actually determines whether coherence is preserved or whether it decays, like typically on a very short time scale, like femtoseconds, I say. And if you take a typical trajectory-based method, you no longer have the notion of this overlap of these wave packets, which is the reason why like these coherence properties are not captured correctly by the classical trajectory picture. So that is essentially the reason why we're going to do something more complicated. Okay, so with this, we're going to move to some examples. And the first is about intra-chain exciton transport, coherent or diffusive. So we want to look at exciton migration. We want to develop like an unbiased picture of exciton transport from this perspective of real-time quantum propagation. We want to compute diffusion coefficients in this picture. And of course, this is meant to establish benchmarks for more approximate methods. And so this is actually not a sketch. It's a representation of our real data that you will see later again in a somewhat different form, right? This is actually the exciton, that is moving in a fluctuating landscape that is generated by torsional modes. And you actually see that the exciton is kind of looking for something like a minimum energy path in this fluctuating landscape. Now, we started very simple. So we wanted to understand exciton migration guided by conformational dynamics, and we wanted to start at 0 temperature and just with a single torsion. So we just wanted to understand, like if you have this type of system, and so we are thinking of a torsional defect that is relaxed as a function of time. Like, how does the exciton adjust to that? So imagine we have a partially localized exciton here on one side. So how is it influenced by the torsional motion? And is this coherent or is it a hopping type step? And essentially we can use something like the Frenkel-Holstein Hamiltonian, but for our purposes, we will adapt the Frenkel-Holstein Hamiltonian to be a bit more precise. And for that reason, and because we have like these large amplitude motions associated with the torsions, we use potential energy surface cuts that we are going to map onto this lattice Hamiltonian that takes a tridiagonal form, so with nearest neighbor couplings, just like a standard Frenkel-Holstein Hamiltonian. And we actually use a mapping procedure here, which is analytical. It's actually very close to like thinking of a Huckel type problem. So, if you have a Huckel Hamiltonian, then you have everything analytical. And this mapping scheme, which is actually an exact scheme, really works like this. So imagine that you have the Huckel eigenvalues, these are the lambdas here, and you want to translate them back to the diagonal and off-diagonal parameters in a Huckel matrix. So that is essentially what we're doing. Now, it's far more complicated because we look at everything in dependence on the coordinates. But still, that's essentially the procedure. Now we come up with an ab initio Frenkel-Holstein Hamiltonian that essentially looks like the original Frenkel-Holstein Hamiltonian. We have nearest neighbor couplings, but now all the parameters are dependent in a non-trivial way on these coordinates that we got from the electronic structure. And we have a kinetic energy that's a little bit more complicated because we have curvilinear coordinates. So actually this Hamiltonian is like a one-to-one mapping from like the actual potential energy surface cuts that we computed. Actually, we computed this at the level of ADC2 calculations, so high-level electronic structure calculations. And we see here for the torsion that obviously everything looks pretty unharmonic. We also see that characteristically in the excited state, the torsion is going to planarize. So we have a steep potential here, the torsion is going to planarize, and this is going to drive the dynamics if we start like from an initial twisted geometry. And then we have these intramolecular and intermolecular bond distance modes. And this is encoded in the Frenkel-Holstein form of the Hamiltonian. Now with this, we do this MCTDH dynamics, more precisely multi-layer MCTDH. This is not too big as a calculation, up to 50 modes and 20 Frenkel type states. We start from this twisted geometry and we look like what happens during the first 150 femtoseconds. Now we see that, not so much is happening, but, so this is the exciton, it's partially delocalized to one side of the torsional defect and it's actually staying there. But we see that the high frequency modes, these X and Y modes, which are actually the CC stretch type modes, are adjusting to the exciton. Actually, we see that there is exciton trapping that appears within a time scale of like 10 to 20 femtoseconds. And these modes are actually going to have like the lattice distortion at the places where the exciton is located. So we see this trapping effect and it's dynamical. The other thing that we see is that we have this transition dipole autocorrelation function, which decays extremely rapidly. And that is actually a contribution to the experimentally observed anisotropy decay, which is of the order of 40 femtoseconds. Now the torsion doesn't do much on the time scale of these 150 femtoseconds. But if we move to 1 picosecond, we see something really interesting, because now the torsion is going to planarize as it should. And so we start with this initially twisted torsion, now it's planarizing on this time scale of 500 femtoseconds, and we see that interestingly, the exciton is following the torsion. It's like adiabatically following the torsion, and it's settling down at the center of the lattice, which is of course what we expect with the relaxed torsion. Everything's flat now, so we have the planar geometry. And we see that the high frequency modes just follow the exciton. And so we really have an exciton polaron species that is moving. We also see that the degree of trapping depends a lot on the high frequency mode. So on the right-hand side, we actually left out the most strongly coupled high frequency mode. And we see that the exciton is becoming much broader, much fuzzier, delocalized. So these trapping effects really depend on the vibrations. And so now let's take a look again at the electronic structure side to understand what's happening. We have these electron-hole maps for transition density analysis, and we look at the conformational dependence, so the torsion dependence. We have like the two lowest adiabatic states, S1 and S2, and these look like particle in the box states, as they should. Now, at the twisted geometry, 90 degrees, we see that, as we hinted at before, so we have this conjugation break. So the density vanishes at the center of the lattice. And then, as we relax the torsion, we go to this planar geometry where we have the local exciton ground state expanding over the full lattice, and the S2 state has the node structure here, right? So essentially, in the dynamics, we start with this twisted geometry with a coherent superposition of S1 and S2, which gives like a left localized or right localized state, and that's going to relax to this local exciton ground state. So to sum up, we have a 2 timescale process that we observe. We have a very short timescale where the trapping actually happens, like 20, 30 femtoseconds or so. And then we have the slower timescale where the exciton follows the torsion. And we have strong reorganization effects, actually mainly from the high frequency modes, but also to some extent from the torsion. And we have kind of this quasi-stationary trapped exciton species. Now with this, we go to final temperature. Now we use like the stochastic driving that I described before. This is at 300K, and we have a stochastic ensemble here. And now all torsions are active. Actually 19 torsions on a 20-side lattice. And we have a far larger number of modes. And these are like individual realizations, like stochastic trajectories that are fully quantum. And we see that the exciton is kind of driven across the lattice now. And so the second panel here is actually the same data as we saw before in the more fancy representation. So the red line is actually the mean trajectory of the exciton. And we see that this sort of adjusts to a minimum energy path in this fluctuating torsional landscape. And we also see that the high frequency modes just follow the exciton. And so this is the technical setup. This is the multi-layer tree that we're using. And right. And now we're using this to compute diffusion coefficients. That's the idea. So we have many realizations now. We actually compute mean squared displacements, fully quantum, and we get diffusion coefficient estimates. Actually, we do this either without or with periodic boundary conditions. And we see that the MSDs differ very significantly depending on whether or not we have periodic boundaries. So the full lines are with periodic boundary conditions, the dashed line without, because in the absence of periodic boundaries, our lattice is pretty small and the exciton is going to bounce back from the boundary of the lattice. We also see that the MSDs and the resulting diffusion coefficients are going to increase with temperature, which is what one sees experimentally. This is a thermally activated process, actually, due to the torsions. And so we also see that the behavior is more or less linear after a transient period. So actually we are sort of in a normal diffusion regime, despite the fact that what we actually see is like coherent type exciton motion. Now, in fact, so this is multi-layer MCTDH down here with Ehrenfest. So I'll say more about that in a second. So we use approximate Ehrenfest calculations to go to larger timescales. Also, I should say that to start with, we have no static disorder, which is why the diffusion coefficients are too large, of the order of 10 to the minus 2. So in the reality, it's more like 10 to the minus 3 or 10 to the minus 4. Okay, so this comparison with Ehrenfest dynamics, actually pretty interesting, because in a sense, this dynamic is kind of mainly adiabatic. You know, it's like mainly on this S1 surface, but not exclusively. So when we do Ehrenfest calculations, it doesn't look so bad. So this is actually for two identical initial stochastic conditions. So it's the same like trajectory. And we see that the Ehrenfest calculations are doing quite a good job. But in fact, we have these very high frequency oscillations, which are due to the fact that there are actually electronic interactions between S1 and S2. This is an artifact of Ehrenfest. Still, we do compare with Ehrenfest dynamics. It's very noisy, but still it sort of, globally makes sense, which allows us then to go to much larger timescales, 50 picoseconds. We include static disorder and we get diffusion coefficients as a function of static disorder. And this finally actually gives curves that compare quite well with what is known experimentally. Now, to summarize this, excuse me, for summarizing just another remark, so this is another system. So we had these oligophenolphene type systems before. These are OPVs, oligophenol and vinylins, with a somewhat looser exciton. This is actually a situation where the non-adiabatic effects become much more pronounced. So we see this because we have much larger instantaneous changes here in the inverse participation ratio. And we also see that the excitons, sort of show a jump-like behavior, a bit like in the Ehrenfest calculations where we have Anderson localization due to the static disorder. So everything depends really on this this interplay between the Electron-Phonon parameters, the electronic couplings, and the disorder. Now, the overall picture is that the intrachain dynamics is coherent and diffusive. We essentially end up in a normal diffusion regime. And we should think of this as like diffusion of these trapped polaron exciton species. So it's coherent, but it's not band-like. The torsions act as a dynamical barrier between like quasi-stationary exciton states. And the spectra, in a sense, can be connected to transient localization theory that has been discussed a lot already. It can also be connected to like adiabatic entanglement transport. Actually, we have this quasi-stationary exciton polaron that sort of essentially follows the torsions quasi-adiabatically. And so for lack of time, I didn't point out that we actually computed the entanglement. So we actually do have like this entanglement transport, which is another mode of describing what we see. In fact, so this general description from Breda and Silbri, like excitons surf along conjugate polymer chains, certainly true. But our picture is actually still a little bit different. Like we have this, this adiabatic following. So we have infinitesimal steps in a sense. Okay. So with that, I will move to the second application. And that is about the mixing between Frenkel and charge transfer excitons. And we're going to start with a system that is actually close to what we talked about before. So these are oligophenolphenes, but now we're looking at this H aggregate, stacked type species. And it turns out that in these systems, there is a significant mixing of the Frenkel manifold with the charge transfer manifold. So we have charge separation between the chains. And here we actually use ADC2 like a high-level method, and then we continue with TDDFT, which gives very, very reasonable results. Now, this study was triggered by experimental observations from the Leonau group, which shows that there is ultra-fast formation of these polaronic species, of the charge-separated species, and they saw that there are striking, persistent oscillations. And so we wanted to understand both, like the emergence of the charge transfer states and the origin of these very striking oscillations, given that we have a system with a very large number of degrees of freedom. So we start with the electronic structure side. We see that so even at the Frankel geometry, we see this very strong mixing between Frankel and charge transfer states. So we go actually to S5 as the bright state. And so this bright state now contains a significant admixture of charge transfer states, which actually makes that we get a significant distortion of the excitonic distribution over the lattice. This is very much in line with what Frank Spano has seen for these systems. Then we get information about the vibrations, this time in terms of a spectral density. So we actually use the full set of vibrations here in terms of the shifted harmonic oscillator model, and you see that the spectral density strongly peaks around 1600 wave numbers. So these are like these collective carbon-carbon stretch type modes, and this also suggests why we actually see these 25 femtosecond oscillations. Now we wrap all this up in this Vibronic lattice model with actually a large number of states and modes, actually up to 200 modes, reduced a little bit in a second step using a dimensionality reduction scheme that we have. And then we actually look at the dynamics using multi-layer MCTDH. And we see that actually, there was a redistribution of density between the Frankel type states, these are the red ones, and the charge transfer states. So actually you see that the density is going to move to the center of the lattice. And we also see throughout the simulations, the persistence of these very high frequency modes, 25 femtoseconds, so very much as in the experiment. And these are the current stretch modes. Now, different picture of the same observation. So here we actually have this density representation of our lattice. And we see that the exciton is generated in the electronically excited state. And then there is this transition, and finally it is concentrated at the center of the lattice. And we also see that there are collective vibrations. So there are synchronous movements of the vibrations across the lattice, which sort of makes an amplification factor between the vibrations and the electronic density. Now, same picture here, but in a complementary representation, we have an adiabatic view of things. And we see that the initially populated S5 state, so the H aggregate, the highest state is the one that is populated, decays very rapidly through internal conversion. And we see that the lower states are populated. So it's a relaxation process on this lattice, actually at 0 temperature, and we're now moving to higher temperatures for these systems. Last aspect here, so does this charge transfer state formation affect interfacial charge generation? Yes, because we open new channels to the transfer to an acceptor species, here a PCBM type species. This can be included in the simulations, and we actually see that this is a case where the system is vibronically hot, and we rather rapidly populate like these charge separated states at a long range separation. So the green states are the interfacial states, which are dominant, where we also go to charge separated states at larger distance. And this is a typical effect in cases where the Coulomb barrier is actually flattened due to delocalization effects. Now, I wanted to mention in the end that we are also looking at very similar dynamics in a very different time regime, very slow dynamics. So this is about cold electron-hole dissociation, in contrast to the previous example. This is a very different system. These are actually self-assembled donor-acceptor co-oligomer systems that are based on PDIs. This is collaboration with the synthetic and spectroscopic groups in Strasbourg and with Gabriele Davino at the Institut NEL. And so we want to look at the electron-hole separation, starting with an electron-hole species that are sitting on one of these diodes. And then it turns out that the electron mobility is so much larger than the hole mobility in the system. So we think of like the electron separating from the hole. And Gabriele undertook a microelectrostatics analysis. So this is the electrostatic potential. You see this very, very striking quadrupolar structure here. And with that, we actually carry out quantum dynamics, actually going to rates which are pretty slow. So this is like, a process that takes nanoseconds. And we actually use a flux overpopulation model in order to compute like first principles, quantum dynamical rates that are generated for a slow process. So that's it. The take-home message is that quantum dynamics is sort of getting there. So, even if it's challenging as compared with trajectory-based methods, it's useful to do quantum dynamics. They work very well together with these ab initio-based lattice Hamiltonians, which sort of contain the right physics, can actually be, combined with various topologies, canonical intersections, multi-exciton states, and so on. Very nice area for using neural network fitting too. And we can provide benchmarks for on-the-fly dynamics. And actually, I should also say that you've seen before that, like these trajectory-based methods also tend to use like fragment-based representations. So all these methods at some point are going to merge with the idea of getting the best out of these different approaches. Now, all this works because multi-configurational methods actually reach large system sizes. And there are actually various types of such methods. Maybe some of you have heard about matrix product states, very closely related to MCTDH. So these methods are now ready to go for these large system sizes. And from what we see, we would conclude that exciton dynamics is, in general, not adequately captured by standard topping models. So we have seen this coherent exciton polymer quasi-particle motion for the intrachain process driven by the fluctuations of soft modes. We've seen coherent formation of charge transfer excitons, and we've also seen that we can use this for various regimes going from hard to cold exciton dissociation. Just to thank the people who've been involved, people from my group, and also various collaborations in this area, and thank you very much for your attention. This is our group in a not entirely up-to-date picture. Thank you very much.
Irene, thank you so much for such fantastic talk. And we have about 4 minutes for questions. And in the chat, we already have a question from Kirill. Did you maintain your method in a code?
Yes, actually, so this multi-layer MCTDH is available in in a public code. Actually, so the version that is available, in contrast to our development versions where we do various other things, the version that is available is actually from the Heidelberg group that originally developed the MCTDH method. So I'm very happy to actually put the reference somewhere. So it's publicly available, and I think that it helps a lot to get an introduction by people who are using this method. It is user friendly, and yes, you can get to the point where you're able to use it.
Yeah, so from my perspective, look no further than Heidelberg in MCTDH code, and frequently they are making tutorials, some small workshops where one can get exposure.
Yes.
So the next question is from Felix. Did you perform any more detailed comparisons between Ehrenfest and ML MCTDH?
Yes. Actually, maybe just another quick remark on the previous thing. So we have development versions involving Gaussian wave packets. So this will become publicly available at some point as well. There is actually the Quantix code that is maintained at UCL by Graham Worth, that shares this Gaussian-based method. So this is another source for MCTDH. There are several ways one can go. Now, the question by Felix. Yes. So one important thing was that our early efforts to include zero-point energy really failed. So if you use Ehrenfest, do not include like zero-point energies by Wigner sampling, because this overheats the system. And then we had to do something, some of these usual tricks in order to escape the problem about, the detailed balance issue. So this is a process where we are kind of, to 80% kind of moving on the S1 surface, but we interact with the S2 and the higher states. Ehrenfest would overheat the electronic subsystem, would extract energy from the phonon modes and overheat the electronic system. And so we actually build in a relaxation effect, not too strong, but this and discarding the zero-point energy was what generated decent calculations.
So the next question is from Smuruti. How the OT lengths affects the CT and Frenkel excitons? Suppose we consider the Fullerene and OT.
Yes, so it does. So actually the simulations I showed were for this 5-side lattice. But so since one of the referees for our paper asked exactly the same question, we actually carried this out for the supplementary material, and we went to, system sizes up to 20 units. And so interestingly, it turns out that due to this mixing of the bright state, which has Frenkel and charge transfer contributions, so there is this effect that actually the density kind of moves towards the kind of the edges of the lattice. Very different from a standard H aggregate. We would have argued that kind of we essentially have like this delocalized exciton sitting at the center of the lattice. Now, qualitatively, this didn't really affect the degree of mixing or so, but we had the impression that these mixed Frenkel CT excitons kind of, tend to split up into portions that are even more localized, at like 2 or 3 units or so, in contrast to the Frenkel case. So we have a detailed study in the supporting material.